and once again welcome to this series of video lectures on organic spectroscopy. For the last 3 videos we have been doing some past problems set in the Indian NET GET examinations, but today we'll make a deviation. I will present before you a little advanced level problem which was set in one of the coveted universities of US, the University of California, Irvine, UCI. And I got this question from the internet source, from the UCI Open, and that question was set by a distinguished professor of chemistry, James Nowick of UCI. And when I saw the problem, I was really amazed that how he could create such a interesting, tricky question from a very, very small molecule, simple molecule. You will see. And that he set in his first year PhD examination. So let us start to discuss about that single problem that was set by Professor James. Thank you, Professor James. We are discussing your problem, how interesting it is. Now see, I'm just reading it out. Analyze the spectra and solve the structure of a molecule with the chemical formula C3H8O3. It's a very simple molecular formula. The IR spectrum shows a broad peak centered around 3286 centimeter inverse. So this clearly proves that it has a OH group, right? And 100.6 megahertz C13 NMR and DPT spectra in D2O show only one CH resonance at 62.8 ppm and one CH2 resonance at 72.3 ppm. Let me tell you, those who are watching who are not advanced level students, graduate students or PhD level students, they do not know about DPT, then let me tell you that in DPT, distortionless enhancement by polarization transfer, that experiment is conducted to know how many CH3 carbons, CH2 carbons, CH carbon, that is methyl, methene, and methylene and methene, CH, and quaternary carbon, they are present. So to know that, we conduct the DPT experiments. I'm not going to discuss about the DPT, but from the DPT, we learned that there is only one CH carbon and one CH2 carbon. Now there is a suspicion here. It's a saturated compound, CnH2n plus 2, C3H8, no double bond. The unsaturation number, as we call double bond equivalent, is 0 here. We shall write. This is the straightforward question that I have copy pasted here, that was set in their examination. University of California, Irvine. Right? So now look to the formula. It is saturated. It has OH group and it has got only one CH carbon and one CH2 carbon. That is revealed from DPT C13 experiment. And now the 400 megahertz proton NMR, because that is the equivalent, carbon 13 equivalent is this much, nearly 4 times less resonance conditions. So 400 megahertz proton NMR in D2O is attached. It only contains 3 multiplets, A, B, C. I will show you, don't worry. Now you have to identify the structure and assign all the ppms, proton resonances, and also you have to give calculate the J values, the coupling constant values from the data sheet. Now these are the three proton peaks at 3.82, the most downfield peak. And you have to explain what is the description of that peak. Doublet of a quartet or triplet of a triplet. So you have to describe the peak pattern. And then if it is a doublet of a triplet, or it is a multiplet of a multiplet, you have to give 2 J values. If it is a multiplet of multiplets of multiplets, then you have to give 3 J values, right? So all these three peaks, you have to express its peak pattern, peak nomenclature, as well as the J values, and also provide the J values JAB, JAC, JBC separately. This is James Nowick, professor of chemistry. Now again, the same compound was taken in another solvent, DMSO-D6, dimethyl sulfoxide deuterated, and an impurity peak at 3.44 ppm was observed. So it is saying that it is due to water impurity. Now explain the difference in the number of resonances. Instead of 3, here we are getting 5 resonances. The earlier 3, these 3 have been slightly changed their positions, and these 2 were not there, but we are getting here in DMSO the same compound. These are the 5 proton peaks in DMSO D6. Now it's saying that 3.44 ppm peak you have to ignore. It is due to water impurity. Now you have to also assign all these peak nomenclatures along with the J values, and also write down here. And this question, as I was inclined to believe that it was for 20 marks, and the time was unlimited. The students can take any length of time, but they used to take 3 problems of this type they have to solve in 2 to 3 hours, and that's it. One of the problems I'm just explaining today, right? Now this is the proton NMR peak spectrum in D2O. And these are only the 3 peaks, and this is the expansion of this one, and you are not able to read out in the integral peaks. This is 1, this is 2, this is 2. It's written 2.17, 2.15. So they have been rounded up to 2 to 1. So in the ratio 1 to 2, this represents 1 proton. There's 2 protons, there's 2 protons. So this, when we see the expansion, we find there are 9 lines, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9. If the number of components, lines is 9, then it has to be most likely a triplet of triplets, TT, a triplet of triplets. Then only 3 3s are 9, otherwise DT, QD, they won't give you 9 lines. So triplet of triplets, this looks little weird unless we see it more carefully. We can't find the proper triplet of triplets, 3 triplets, right? Now you see here, if you very minutely observe this 9 lines, you'll find this is the first triplet, 1 is to 2 is to 1, this one, right? And the second one starts from here. It is coming to the left of the last line of the first triplet. So this is the first line, and it's 1:2 because that was the first triplet 1:2, and the second triplet of 1 is 1:2:1. The second triplet of the 2 is 1:2:1. That is 2:4:2. So that these are the 3, and the corresponding one is here. This. And the last triplet also has been, crossed the rightmost component of the middle triplet. So this is this one, first component, 1:2:1. Now this one has crossed the first triplet, and this one has crossed this one has crossed the middle triplet, because the crossing has been possible because the J values are very close. If the J values are very close, 6, 4, 5, 6, 7, 6, in that cases there will be crossing of components, and it will be, unless you become very careful to find out the components, it will be very, very difficult to find the J values. These are the 9 lines. You don't find a triplet of triplet. Had it been J values are widely different, then it would be looking like this: a triplet and a triplet and a triplet. So the first triplet is 1:2:1. Each component is a triplet 1:2:1. This is 2:4:2, the 1:2:1. So this looks like this. But because this one has come before this one, and this one has come later than this. This one has come later than this one. This has come to the left, this has come to the right. So this crisscrossing of components has happened, which will baffle us unless we see it very, very carefully. Now these two are double doublets. Very, very simple. No ambiguity. This is a DD, doublet of doublets. This is also doublet of doublets. Of course, they have lost a bit of the first order nature that happens when the peaks are close. Then the first order nature is slightly compromised. We have to bear with that. Now the interesting thing is the formula is C3H8O3. There is only one functional group OH. This is on saturation 0. Functional group is nothing other than OH. So and we have only one CH and one CH2 revealed from DPT, depth distortionless enhancement by polarization transfer. You forget about that if you are not familiar with this term DPT. So one CH2 and there are 3 oxygen. So it seems that this is the compound glycerol. So when I took this problem, my immediate guess was it is glycerol. There cannot be. But the question is, only one CH2 is coming because these two are equivalent. For DPT, it will not distinguish between the different non-equivalent diastereotopic protons. It will only say that a carbon is bonded to 2 hydrogen, CH2. So because these 2 carbon atoms are equivalent, so it is showing one CH2 peak and one CH peak, right? But we have in the proton peak, we have 3. One for one of the diastereotopic proton, which are equivalent here and here, and the other is for the other diastereotopic proton, which are equivalent here and here. I'll show you. Just hold on for a moment. Now, these are the data. I will show you how you have to make a calculation in an easy manner by using your Excel software. In a spreadsheet you have to do, you have to take this data, because every computer spectrum will be associated with the data set. This is the ppm value of every line, the corresponding frequency value with respect to TMS, and this is the intensity value, relative intensity. And from here you can have a guess, because you have to compromise with the pseudo first order nature of these spectra, these peaks. So, but in a very generalized manner, you can just know it is 1:2:1 or 1:3:3:1. You can just have a prima facie evidence of the peak that you are referring to, the components which are being distorted, superseded one peak by the other peak. You can know that from here. Now I have highlighted 9 data to represent the 9 lines of the TT, triplet of triplets, right? This one. Starting from the downfield position to the upfield position, we are going. This peak we have analyzed, we have seen, and the doublet of doublets. These are the 4 data, and this again is a doublet of doublet, 4 data. Now this represents 2 protons, and these 9 data correspond to only 1 proton. Now this is DMSO, where you find the complete change. There are 2 additional proton peaks at a downfield region near about 4, a doublet and a triplet, the ratio 1:2. This is the integral. I'm writing down, it's not visible here to you, so I'm writing down 1:2, and these 3 are analogous to these 3, but they have been more conglomerated, jumbled up, so that the first order nature has been more compromised, and you find these 3 peaks will be there. But this time, if you go for the expansion, you find this one is no longer a TT, as we found 9 lines. It is a symmetrical sextate, 6 lines. Just count down 1, 2, 3, 4, 5, 6. It is already written in the spectrum in the question that this peak they have identified is due to some water impurity that is present in the DMSO D6. Water impurity present in the DMSO D6. So this we have to discount, right? So this looks to be an apparent sextate, and this peak contains apparently 5 lines. This peak also contains apparently 5 lines. You will see, you yourself will see, and tell me if you are really involved in this discussion. You'll tell me it cannot be 5 lines. Some merger, some coalescence of components, some lines has definitely happened, so that the number of lines has been reduced. You will tell me, and we will find out with our bit of common sense the J values, and we shall try to average it and present before the examiner, Professor Nowick. Now in DMSO we have this doublet, 2 data, this triplet, 3 data. These are symmetrical. We consider it symmetrical, although there is some dissymmetry, but we ignore that. It's not a simulated spectrum, it is a real spectrum. In simulated spectrum, in some software like ChemDraw, we can get a very cozy looking, very good looking spectrum, which we can present before the students for study purpose, for beginners to understand. But the real situation is not the same as we often get in a simulated spectrum. Now, then this 6-line asymmetrical sextet, these are the 6, and I ignored this 3.44 data. It is saying I have ignored per water impurity. You may ask me, why did I not ignore this 3.4459? But which is more close to 3.44? Is it 4.4459 or 3.4383? And moreover, this has an unusually high intensity, which does not go well with the pattern 1:5:10:10:5. That it doesn't go, because a 6-line comes under the Pascal triangle, so that ratio doesn't at all fit into this. So I took this one is for the impurity water. So excluding this peak, we have 6 lines: 1, 2, 3, 4, 5, 6. And these are the, as usual, this not as usual. In that case, it was a DD. Each one is a DD, but this case contains 5 lines. But you will tell me it is not really a quintet. It is something else. Just hold on for a moment. So this 5-line data, 1, 2, 3, 4, 5 line, is for this typical 1, 2, 3, 4, 5, and these 5 lines 1, 2, 3, 4, 5, and this one. I have separated them. Now, the only data, this one for the D2O, it has not been shown in the graph. So this definitely is there somewhere 4.7, that is out of the range given here. So indicating that this is also due to the impurities. So the question is not at all bothering to think about it, because it is saying that there are 3 proton peaks. So we have to ignore this 4.788 peak, which is due to some, I'll tell you due to what, I'll tell you later. Let's see. Now, I've tried to explain to you. The first one is D2O, proton NMR. We have already told that it is a TT. This, and this is one triplet. This, and this second triplet. This, and this is the third triplet. This one expanded. This is a DD. This is a DD. This is a TT, right? Now, I have already told you about the IR and the DPT. There is no point in wasting time. 3 peaks, I have already told you. Now, the beauty is when you take a particular compound in D2O, the labile hydrogen atoms like OH, NH, they are substituted by deuterium. They exchange with the deuterium, and deuterium has a strong bond with any atom than hydrogen. So when it is deuterium, there is no longer hydrogen. So there will be no proton peak. We are not observing deuterium. We are observing proton. So this OD of glycerol, that will not show any peak, right? But there is no impurity peak here, but yes, the small little peak which is not given in the spectrum, which we have ignored, might be due to some of the OH which is remaining as impurity, not completely substituted, it is remaining. So that is giving, so it's so weak intensity. We can look to the intensity, this one. Of course, intensity is quite high, but even then we have ignored it, because we know that we have deuterated the sample. There should not be any OH peak. Therefore, we presume that it is due to some impurity, so we have ignored it. Now, I have this one is OD. This is HA. It is 3.82 TT. Why it is TT? Because it has two different coupling constant. One coupling constant with HB. This HB, they are equivalent. These HC, they are equivalent under symmetry operation, plane of symmetry. At the midpoint, passing through this carbon, this OD, and this HA. And interestingly, this CS2, these two protons are diastereotopic. Can you tell me why? If you already know something called prochiral center, supposing you have a compound like this, CH2, and supposing this is X, and this is CHOH, and this is CH2, and this is same X. So this is not a chiral center, no doubt about it. Had it been a chiral center, you would have shouted that these two are diastereotopic, non-equivalent, so also these two. And one of them from here is equivalent to one of them here on the same side, and the other one from here and the respective one, the corresponding one here also would have been equivalent. You will say, no, this is not diastereotopic because this is not a chiral center. These two groups are same. But, you know, these types of molecules have prochiral center. This is a prochiral center because, interestingly, when you substitute any other group, say deuterium, then you will kill two birds in one stone. You not only create a chiral center here, this one automatically becomes a chiral center. So this is one diastereomer, and if you substitute the other hydrogen by the deuterium, you will get another diastereoisomer. This remaining fixed, you are changing. So the prochiral center, the CS2 at the prochiral center, they are really diastereotopic. Therefore, these two are equivalent, non-equivalent. These two are non-equivalent. They couple with each other by J2 coupling, but these two are equivalent. So one of the rightmost peaks is due to these two, and the extreme, rightmost peak is due to the other one, CC, 2 proton in 3.60, and that is a DT because it is coupling with a J2 which is greater, more than 10. J2 is greater in sp3 hybrid carbon, and it is also coupling with J3HA. So this is a doublet of doublet. This is also a doublet of doublet, DD. And these two are equivalent, these two are equivalent, so you are getting 2 proton DD, 2 proton DD, and this HA at the downfield position is a TT, because for HA all are J3, 1 2 3 1 2 3 1, and coincidentally, accidentally, all these values are not same. Had it been same, in many cases, due to rapid rotation, in many cases J3 values are same. So had it been same, then 2 plus 2 plus 4 plus 1 5, it would have been a quintet. 2 plus 2 5 plus 1 quintet. But since the JAB is different from JAC, so first, supposing JAB is greater, say 7, so it will be splitting into a theoretical triplet by these two, and each of the components will be split into another triplet each by these two equivalent protons. So it will be a triplet of triplets containing 9 lines, right? So I will tell you how I have used the Excel spreadsheet to find out the J values. There are two J values here for the 9 lines TT. One is a small j, the other one is a big J. Small j is between the two immediate adjacent components, and the big J is between the midpoint of the first triplet to the midpoint of the second triplet, or the midpoint of the second triplet with the midpoint of the third triplet. Now, how we have done it, I'll tell you. So if you have not learned how to find the J value of a multiplet of multiplets, then my suggestion will be to number them in a very sequential manner, in a serial manner, all the components 1, 2, 3, irrespective of whose line is this. Is the line for the middle triplet or the first triplet? Doesn't matter. From left to right, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? Now the small j1, first you have to find out. It is between the adjacent components of an individual triplet. So it is 1 to 2 or 2 to 4. We already know that 3 is belonging to the middle triplet. So 1 to 2, then 2 to 4 is another value. Then 3 to 5 is another value. Then you have 3 to 5. Then you have, 5 to 7. You have 6 to 8. You have 6 to 8. So you can have 7, 5, 6 values for getting the J small. But how to get the J big? J big, from this is the midpoint of the first triplet, and this is the midpoint of the second triplet. So from this to this, or if you go 1 plus left, then you can go 1 plus left. Right? So 1 to 4, or it will be 2 to 5. So that will give you the big J value, 1 to 4 or 2 to 5, because we want more number of J values of a particular type and average out so that we get least error. Standard deviation will be less. So in this way, we have found out using a Excel spreadsheet. This is the 9 lines. The first small triplet, the component, 2 components are immediately there, and the third component is crossing the first component of the middle big triplet, and then this is the big line of the middle triplet, and the small triplet of the third small triplet. The first line is here, and the last line of the middle triplet is here, and the last 2 lines is here. So we have taken this, this minus this, or this minus this. If I show you the Excel spreadsheet, how we have done, if you can see, then this is D2O and C. Here you find this is V3 minus V4, these two. And here it is not B, because the next line is here. This is B4 minus B6, this minus this, right? And then you can also go for this and this. This is B5 and B7. And you can go for this and this. This is this and this. That is B7 and B9. You can go for this and this. This is B8 and B10. And you can go for the last two. Just like first two, last two. And we take an average. So the small j we find first, it is 4.37, something, forget. Then how to get the big J? You go for the midpoint. I told you the midpoint of the first triplet and the midpoint of the second big triplet. This is B4 minus B7. B4 is the cell number, I mean this row number, but actually it is the component 2, marked 2 minus 5. So if you look to the graph, it is 2 minus 5, the midpoint of the first triplet, the midpoint of the second big triplet. Similarly, the second big triplet and this one, the midpoint of the third triplet. So we found out this. I am not going to show you anymore. This is the big J value and I have taken the average. Now see how close they are. That is the reason why the crisscrossing of components was happening and it was looking weird, and we were taking a lot of time to really locate where are the components and how to get J1 and J2. I mean J big and J small. Now this is very simple. DD is very simple. I show you a DD here, doublet of doublets. This is the small J, this is the big J. So you, in the same manner, number 1, 2, 3, 4, difference between 1 and 2 and 3 and 4, they will give you the two small J values and you can average. Similarly, you, to find out the difference between the two midpoints, you can go for two values. You go, half place to the left, you go half place to the left. So that 1 minus 3 will give you one big J value. Similarly, 2 minus 4 will give you the other big J value. So we can average out. We have done that and we have found out, this is the small J value. This is this is a small J value, 6.52. This is the big J value is 11.69. Understandable, because this geminal coupling is more stronger. I mean, it's stronger than the vicinal J3. So we have got it. That's very interesting. And this is about 6.5. The average is here. This is the J3. This is the J2. And all the average values have been given here. So this is all about our work on, in the D2O spectrum. But one thing is sure, that you can't say whether this is 3.60 or this is 3.60. This is 3.69 or this is 3.69. You can't say unless you go for the 2D NMR analysis. Which one is closer to HA? Then that will tell which one is which. But for now, we can assign anyone to 3.60, 3.69. Doesn't matter. Now, let us go to discuss about the DMSO. DMSO, what has happened? The common sense is, this compound, when we have, and while I was solving this problem, this was OD, this was OD, and this was also OD. When there is no D2O, it will remain as OH. It will be remaining as OH. Only and D2O there is exchange and there will be OD. There will be no OD. DMSO is there is nothing deuterium. But that D6 is not exchangeable deuterium. So D2O D is exchangeable with OH, but DMSO D6 deuterium is not exchangeable. So all these are in their original OH format. And if it is a pure one, maybe Professor Nowick has taken a very pure sample where the acidic impurities are almost minimized. The exchange rate with impurities is very, very less or slow in the NMR time scale, so that this proton is able to couple with the neighboring protons and being coupled by the neighboring. This will couple to the neighboring protons and the neighboring protons will also couple to this. So you are getting, two OH proton peak. One OH proton peak is here at the extreme downfield. Is a doublet because of this J3 coupling. We will find out all the coupling constants. And these two are equivalent. And their integral ratio is 1:2. And that is a triplet. Why? Because there are two protons. Although these two protons are non-equivalent, but accidentally for this OH proton, they have similar J values. So it is a triplet. Accidentally, they have similar J values. So it's a triplet. So these two protons will be having a triplet. But the A proton, this is the A proton, this is the B, this is B, C, C, and this is supposing X, and this is Y, Y. And the question also has given these letters A, B, C, X, Y. Now this A will no longer be a TT. It will be, you can immediately say that it will be a doublet of triplets. Why? Because this one, no, this will be a sextet. I'm so sorry about it. I'm so sorry. Now this one has how many neighboring protons? 2 plus 2 plus 1. 5 plus 1, 6, sextet. And for this, the coupling constants are accidentally same. Although the CHOH has a slightly lower value usually, but in this case it has been found to be almost similar, so that these two and this 5 plus 1, so it is giving almost a regular sextet or a symmetrical sextet, this one. And we can get the J value for that is only one J value. But what about the BB? B will be having a geminal coupling with a larger coupling constant, 10 to 11 like that, and it will be coupling with two neighboring protons accidentally with similar J value, J3 values. So 2 plus 1, 3. So first doublet by C and then triplet by these two, so it will be a doublet of triplets. So also the case of C, these C's are equivalent, these B's are equivalent. So you get undoubtedly a doublet of triplets containing 6 lines. But in this scenario, when they are very close, so coalescence of some components definitely must have happened, so that instead of 6 lines, we are getting 5 lines. But don't worry, we know it has to be a doublet of triplet. So that cannot be, because same compound we have already identified in deuterium, in D2O. We have identified it. Here the only difference is the OH peak will be available, and also the OH will be able to couple with the neighboring protons, and itself being coupled by the neighboring protons. Right now I have given you this data. This is the 6 line one. You have to consider this 1, 2, because the data is given. I am not saying from just whimsically, because the data is given. So the data starts from here, 1, 2, 3, 4, 5, 6. And this word of fig has to be ignored. And then this so-called 5 lines, we have to say it is apparent doublet of triplets, DT. 1, 2, 3. Maybe the triplet 1:2:1, and here 1:2:1, that 1, 1, they have coalesced into a single peak, right? So 5 lines we are getting because of the coalescence of the middle components. So that many times it happens. We have to very intuitively judge, because we already know the structure. It has to be a DT, doublet of triplets. Now we see here, I have shown here the integral values for HA. For HA, here is the structure. HA, the integral peak is showing 1.41 because some additional water peak is there. That is why it is giving an extra integral height, so we have to ignore this 0.41 for the contribution of the water impurity peak, so it is really 1. This sextate is for HA, and this was a 9-line TT in the D2O case. Now it is a sextate, apparent sextate, and these 2.07 is the HB and HC. These are the two non-equivalent protons, diastereotopic protons, BB, CC, and 3.37 5 lines, but it is apparent DT, doublet of triplet. 5 lines, but apparent doublet of triplet. And the HX is the solitary OH in the middle, this is doublet, and the HY2 proton, this, I'm sorry, this HY, that is, oh, I'm sorry, HY, we have done this one. HY, we have shown this one. So HY is 2. The HX is 1. Now, if you can see the spectrum, the HX is 1, HY is 2. So here I have written HX as 1. And this is the integral. The decimals have to be ignored. This is 2. So this HY, there are 2 equivalent OH protons on both the sides. This is the structure. Yes, on both the sides, this and this, they're equivalent structures. It's 2 proton, 4.39. It's triplet. Why? Because these two, they may be non-equivalent, but for OH, the J3 is nearly same, so triplet. And for this OH, only there is J3 for HA, so this OH is a doublet. In the beginning, in the downfield region, gone. Now, using this spreadsheet, we have found out for HX, there is no problem. We have found out from these two, there is only 2 data, doublet. So difference between these two will give you the JAX, the coupling constant between this A and X, the 3-bond coupling constant. It is the list 4.78. And the HY, which are this HY, we have to have 2 values. This minus this minus this. So average is 5.6, which is greater. Then HA, which is a sextate, we have to consider as a symmetrical sextate. So we have to use this minus this, this minus this, this minus this, this minus this. So out of these 6 values, so 5 values, the average is 5.3, right? Now the tricky part is HB. This is the trickiest part to find out the big J and the small j. You know, the big J is the geminal coupling. If we look to the structure, the big J is the geminal coupling between BC, and the small j is between these two. This 1 plus no, this one. This is a 4 bond. This and this, not this one. This is a 4 bond coupling. Doesn't happen. So 3 bond. So 1, 2, 3. 1, 2, 3. So 1 plus 1. So they have similar coupling constants. The small j and the geminal coupling constant is large. So we have to find out by taking these two difference as the small j is easy. We can monitor this graph, this one, the 5 line, these two and these two. These will give you the small j, and from this to this, first to third, that will give you the big J. So we have done that. This is for B. We have got so many values. For small j, it is coming 5.4, and for the big J, we have taken only 2 reliable data. So the average is 10.7, almost. But we have added all these 4 that we have found. It's 21.727, and they double up this big J is equal to the sum of this. So to tally whether our calculation is correct or wrong, we have done this, but we have tactfully used, if I show you the data for the DMSO, for JHB, here we have taken now C, which data we have taken. This is 2022, means 1 and 3. 1 and 3. And here also we have taken 21, 23, means this one and this one. That means in the spectrum, we have taken to find the big J, we have taken to find this one, this one, this one, and this one. Big J, because the coalescence has happened somewhere here. So 1, 2, 1, 2, sorry, these two will give you the small j, these two will give you the big J. These two will give you the small j, but these two will give you the large J, big J. So in this way, we have found out the values of all J values. Now similarly for HC, its partner, geminal partner, we have done the same thing. So the big J, first the small j, the same principle, and the big J. So they are averaged out, all the big J, B, C values have been averaged out, and the average values are the big J is J2 that I have written. J2 is 10.77, that is BC. And all these J3 which are accidentally same will be 5.47. And JX, which is unique, that is a doublet, the only solitary OH in the middle coupling with the CH, that has a different J value. But all other J3, this is J3 also, but that is unique. But all other J3 values are more or less same, and they have been averaged to 5.4, and J2, BC have been averaged to 10.7, and so on. So all these things we have already discussed. The J values have written, the nomenclatures in the D2O, PIC, TT, DD, DD, and their corresponding J values, the average J values we have written here, and also here, and we have explained why we didn't get the OH peak, because it is all OD. But in DMSO, this has been, this is for DMSO. There was no space. This structure is for DMSO. When there is no OD, there is all OH. This is X and this is Y. And we have, in DMSO, coupling of OH proton takes place with other protons with J3, but in D2O, OH becomes OD, and there will be neither coupling nor have any proton peak for the OH group. But a proton peak at 4.7889 ppm might be due to the residual OH, which has been ignored in the D2O spectrum. Now, in the DMSO spectrum, similarly, all what we have already discussed, I have written is a doublet. This is a doublet, and this is it's triplet. I'm so sorry. The second one is a triplet. The first one is a doublet, a triplet. The J value is 5.5, and then it is a sextet, apparent sextet. The J value is 1. Only one J value. But if it is a DT, and this is a DT, the J values are, the big J is written first, the small j is written second, and these are averaged out for the same value, right? So almost we are at the last part, and this again, and this is the problem that was set in UCI Irvine for the first year PhD course. So was it not interesting for you? And whenever here you solve a problem with the spectral data and analyze the J values with multiple J's, J2, J3, and the J3 values are different. You found in the first case, you found the, JAB and JAC, they were not same. Therefore, the 9 lines were, they came so close, they interchanged at 2 places. and we had to use our a little bit of intuition to segregate which one is which. It's going very late. Thank you very much for your patient hearing. I'm sure those who will be benefiting out of this program will like it and put a like you press the like button, and if you have not subscribed till now, please subscribe, because yes, next week there will be no production of from my spectroscopy series because I am leaving for US. So the transit will take some time. So when I'll be settled in US, hopefully from September, I will resume the work. But after this video, for this whole month, I don't think I'll be able to produce any more video on this particular problem series. Give your comments. Bye bye.